So please let me introduce Dr. Martina. She's a geophysics researcher. So please, Dr. Martina, the stage is yours.
Thank you, Abdullah. Can you hear me well, right?
Yes, we can hear you.
Perfect. Let me just share my screen for my presentation. Here it is. And
Yeah, we can see it.
Okay, I can put it in presentation mode. So hello everybody, thanks for joining this webinar and thanks for the invitation. We're so happy to be here. I'm so happy to be here representing GReD. So the title of my topic is about how satellite-based potential global models can help exploration geophysics. I work in GReD, which is a small medium enterprise founded in 2012 as a spin-off company of Politecnico of Milan. And we are based in Italy, close Milan. We have a few areas of business. So we work not only on what will be the topic of today, but we also work on GNSS monitoring applications for structural health monitoring, for example, for pipes, dams, pillars, buildings, whatever can be monitored with GNSS. We also do some research activities on physical phenomena modeling and data analysis. And course, today I will show you something about potential field data processing and analysis for mainly related for geophysical exploration for natural resources. We are 13 people, most of them with a PhD in geodesy and geomatics, and we have our president is an emeritus professor of Polytechnic, acknowledged with various important prizes. Okay, let me move. So let's go to the focus of the webinar. So potential field methods which exploit gravity and magnetic field data are a powerful tool to recover information on the Earth crustal structure. Thanks to several dedicated satellite missions, today we have a large availability of data covering more than 19% of the Earth's surface, with some exception in polar regions. But one of the main challenges today to be faced is to fully exploit these global homogeneous satellite data. And this is something that can be done by merging them with the terrestrial data, because of course gravity and magnetic field can be sensed also at terrestrial level, so at ground, from airborne or ships. And it's also important to use specific processing techniques to combine this kind of data to retrieve the most information as possible, the more powerful information as possible. So it's important the combination of this data because satellite and near surface measurement are somehow complementary and not sensitive to the same geological structures in depth. Just a quick overview about gravity and magnetic. So we have that gravity and magnetic fields data, if separately analyzed, suffer for something called a not uniqueness, in the sense that in the real world, actually, when we observe a gravity data or a magnetic data, we have in the real world different geological structures with different geometries and properties that can generate the same signal that we observed at satellite level or at ground level. But the important thing is that gravity and magnetic are similar from a physical point of view, but they are sensitive to different things, in the sense that gravity is sensitive to masses and density variations, while the magnetic field is sensitive, of course, to the magnetic properties of materials. Of course, when we observe from satellite the magnetic field, we have a dominant signal which is related to the inner part of the Earth. But what is done for application related to the oil and gas sector is basically to filter out the main signal and look to what it's shown in the map on your right, which is basically called the magnetic anomaly. So we look at quantities really small because we are talking about nanotesla, but we can say that these anomalies are related to materials present in the first few decades of kilometers of the Earth crust. I was saying that we have a problem that if we process them separately, we have like a not uniqueness solution to the inverse problem. But a solution to this problem can be to use a joint processing of both gravity and magnetism. This is something on which we work and we currently do for our clients. And this help in somehow reduce the space of possible solutions. I was saying that today we have a wide variety of global data, both in terms of gravity and magnetic field observations, because there have been various satellite missions focused to measure these quantities. And these data have been processed by many research institutions worldwide to obtain what we call global models in terms of gravity and magnetic that can be or be purely based on satellite data, but can also be a combination of satellite data and freely available terrestrial data sets. So they can be provided as grids, as the one I mentioned here in this slide, but there is also something called that we call like a reference repository, in which the global gravity field models mainly are provided as spherical harmonic coefficients. This is like a mathematical tool that can be used to model the global gravity field, and they are really useful because on this repository it is possible to use these coefficients to compute different functions of the gravity field, which are really helpful for geophysical applications. This is just an example of global gravity data interpolated on the grid, a user-defined grid that can be large, whatever we want, of course. So we can just have a map over the oceans, but also, of course, on land and so on. I was saying that one of the greatest challenges is the maximization of the informative content of these gravity and magnetic data acquired at satellite. And this is possible integrating data at different levels. The combination has to be done with methods that consider also the stochastic characteristic of the data, in the sense that we want to model in the best way as possible the variability of our signal. As you can see in the first image on the left, we have a global model, and in the middle, a combined model in which we used three different kinds of data. So one global model offshore, that in this case was the best one, an airborne survey on the coastline, and another model which, as you can see in the central image, had a better signal on the onshore. The optimal merging provides an improved grid in order to infer then, by means of specific joint inversion algorithms, the Earth's lithosphere structure properties. This was just a recap, just to give you an idea about gravity data differences, but similarly, we can say more or less the same thing also for magnetic. So, of course, the more closer we are to the terrestrial level, to the ground, the more higher is the cost of this kind of survey, of this kind of data. And also, we can say the same for the accuracy and spatial resolution. But the most important thing is that when we look at satellite data about gravity and magnetic, we have a wide variety of global grids and global models that, first of all, are the most economic tool that we have, because they are basically for free and available to everyone. And they have a slightly lower resolution and accuracy, but if properly combined with the terrestrial data, can be really helpful for geophysical applications. Just a few examples of possible uses of potential data for natural resources exploration. So they can be used as example for at regional level, for example, in cases where we have few seismic profiles and we want to understand better what are the density distributions or the magnetic properties distribution inside our study area. And in this case, we can integrate with gravity and magnetic and fill these voids somehow. Or other applications are more local, for areas smaller than 100 kilometers per square kilometers. In this case, it can happen that we have a really good seismic derived information for the shallower layers. And what we want to know is what's about the deeper structure. So we want to know something more about the crust and the mantle and things like that. This is something that can be done by using, as I was mentioning before, a joint inversion algorithm. The joint inversion algorithm on which we currently work for our client is a 3D joint inversion, in which the starting point is basically a 3D model. So we collect all the information we have from seismic profiles, well logs, literature, to build a starting point of view, a starting model in terms of geology, so classes, densities, and susceptibility. And then the inversion basically go in an iterative procedure to change the class, the density, and the susceptibility of each element of our volume to maximize the degree of fit with our observations. And the resultant model is something which is realistic and fit the observations and the constraints we had, for example, from seismic. I have just a couple of examples. So this is an example of result of a joint gravity and magnetic inversion. This was a study at a really large regional scale because involved the whole Mediterranean region. But I plotted here in the two images on your left an example of what was our starting point in terms of average crustal densities before the inversion, and what is the result that we obtained after the inversion, the joint inversion. The black lines that you see overlapped in both the images is an information about the crustal blocks, the principal crustal blocks, but it's important to understand that we didn't provide this information to the inversion algorithm. We simply inverted the gravity and magnetic data together, and you can see how the results are extremely coherent with the crustal blocks available from another studies, from another method. Moreover, if we look, since the result is of complete 3D volume, we can have some more details about what are the density variation inside the crust. In this case, we were more focused on the crustal layer. We can distinguish between oceanic, continental crust, which when we are doing studies for natural resources exploration, sometimes it can be really helpful for the following activities. And in this case, our final model was a relevant improvement in the study of the crust, which could be used as a background for further local analysis and studies. This other study was a more localized study, always quite big, few hundred of kilometers, but in this case, we had to first of all integrate the data because we just had some data from a shipborne survey. And for our application and also to study mainly the crust and the sedimentary layer, it was really important to combine them with the global model derived from satellite, because in this way we were able to not only to do some manipulation to the observation to see something that we call other gravity functional as example, on which we can notice the principal faults. So one thing I want to underline that just manipulating our observation, we can have another look, another point of view on some specific problems that we can have in this kind of application. But also, it's important also to notice how good were the results in understanding. If we look at the section profile we have here, some characteristics in terms of density distribution of some sedimentary layers. In this case was the salt that we have in the Mediterranean area. And that basically is made the seismic blind, because from seismic we can usually see the top of this material, but not what's below. So here the gravity and magnetic were really helpful to model and clarify what happened in that area. But it's also really interesting to model the shape of specific feature. In this case was the thickness of the continental crust. And my final slide, the point that I think it's important to remind in the framework of this webinar is that potential field data acquired with dedicated satellite missions have a worldwide coverage nowadays, and they offer a power and economic mean to explore the Earth crustal structure. They refine, of course, the more information we have, the more localized information we have, the more we can combine this satellite and terrestrial data to guarantee the advantages of the different survey methods. And if we apply algorithms like the one I showed you here, so this kind of 3D joint inversion, It is possible to in part to reduce the non-uniqueness of the solution by reducing the space of admissible geological models that fit our data. And we can obtain, of course, a complete volume. So not only the surfaces, but also the density and the magnetic susceptibility distribution inside our model area. So this is something that for this kind of application can be really of help. And with this, I conclude my presentation. So thank you.